we have begun recording this talk, so I will actually introduce Richard again, so it's on the recording. My pleasure to welcome Richard Elwes from the University of Leeds, who will be talking about random graphs in logic and network science. Richard, you have around about an hour, and then we'll have about 45 minutes for questions and discussion. The Q&A will not be recorded. All yours.
Great. Well, thank you very much indeed for the invitation. It's a pleasure to be talking this morning. So the background to this talk, and indeed to myself, for those who don't know me, is I was trained as a model theorist. I did my PhD with Dugald Macpherson in Leeds more years ago than I care to remember. And so I worked in model theory, and like all model theorists, I spent a reasonable amount of time thinking about graphs of various kinds. And then my career took a sort of slightly sideways turn. I actually sort of left the university setup for a while, and for a number of years I worked freelance writing popular maths, popular science books and things like that. And then I sort of slid back into the university world, and for really just a sort of a coincidence, I ended up working on quite a different area of mathematics for a little while. Just from chatting with some friends who just were talking to me about something they'd become interested in, I started working on what you might call complex systems. So there's a whole big area of mathematics where people think about random dynamics on graphs. So this is used to model all sorts of real-world phenomena. And the particular problem that I was working on with some friends was modeling a theoretical approach to racial segregation. But in the course of that work, I ended up sitting in a lot of seminars about people who were using random graphs and dynamics on graphs and dynamics of graphs in all sorts of interesting ways to model various real-world phenomena and just to sort of investigate the sort of huge variety of interesting patterns and configurations that arise. But of course, I still had the sort of model theory bit of my brain switched on to some extent. So I'd often ask questions like, what happens if you take the infinite limit of that process? And people would look at me strangely because in the real world, that's not a thing that happens. That's not what we do. So it's not seen as a useful tool. And I started sort of trying to make some gentle connections between those two worlds, I guess. That's the sort of theme really of this talk, is that in model theory, in logic, generally we have graphs. We're interested in random graphs, but there's this whole area of maths where random graphs and networks are used for sort of modeling real-world phenomena. And I'm just sort of interested in trying to make some small connections and just see where we get on. Okay, so I think I can't start to talk on.
I have a brief interjection here, Richard. Have you advanced your slides at all?
Oh, I just did now.
Okay, because it didn't on the screen.
Oh,
so...
I mean, I just did 1 second. Okay, that's interesting. I wonder why. Maybe it doesn't like full screen.
It could be that.
Okay, maybe let me just.
I know with some programs, it depends on whether you go into full screen before or after you share the screen.
Okay, let me. Okay, thanks for not letting me go on for 15 minutes before saying that. Okay, I'll try again. So I'll unshare and then I'll reshare. So maybe if I go into full screen now. Then I'll try and share. Okay, is that sharing?
Yep.
And now if I try advancing the screen, okay, is that doing anything?
Yes, now it's moving forward. Yep.
Okay, right. Thank you very much, Sarah, for catching that at the right moment. Okay, great. So if I'm talking about random graphs, there's really only one place to start, and that's with the work of Erdős and Renyi. So I'm going to talk about that a little bit at the beginning. I realize this is going to be extremely familiar to a number of people, but maybe there are some people who you haven't seen this before, or maybe haven't seen it for a while. and I'd rather bore a few people than lose anyone. So I'm going to talk about this a little bit. So this is the sort of absolutely standard interpretation of a random graph. So we have some number, p, it's probability, and we have n, which is, well, in principle, it can be any cardinal number, but for present purposes, it's either going to be a natural number or it's going to be aleph naught. And then we have n vertices, which is going to be the vertices of our graph. And then for each pair, we toss a coin, biased coin, and if it's heads, which it is with probability p, then we join that pair with an edge, and if it's tails, then we don't. And that produces a graph, obviously, and it is a random graph because it is produced by this random structure, by this random process. And the sort of model theory excitement comes out of this theorem here, which is that if we do this process on countably infinitely many vertices, then independently of what our value of p is, so long as it's strictly between 0 and 1, then there is a particular graph R which will, with probability 1, arise up to isomorphism. So that's the sort of starting point of random graphs in model theory, I would suggest. So what is this random graph? Well, I'm going to call it today the Rado graph, because it was also investigated by Richard Rado. You will often hear it called simply the random graph in model theory circles, but if I'm talking about random graphs of other kinds, then that's not a good name for today. You might also hear it called the Erdős-Renyi graph. Okay, so what is it? Well, I've heard of this. Its axioms being described as what's called the Alice's restaurant property from this song by Arlo Guthrie, which says you can get anything you want at Alice's restaurant. Any configuration that you might hope to find, you can find. So let's make that specific. So the axioms, or the axiom scheme for this graph is as follows. If you've got two finite disjoint sets of vertices, u and v, then you can always find some vertex which is joined to everything in u and to nothing in v. Okay, so everything I've said is going to be very familiar to most people in the audience. Most of these facts will be familiar too. These are some of the reasons that logicians find this structure interesting. So some of the properties that it exhibits. I'm not going to spend too long on this, but importantly, it is universal for the class of finite and countably infinite graphs. So any finite or countably infinite graph you can find in there as an embedded subgraph. It is countably categorical. So if you take two countable models of the axioms I just described, then they will be isomorphic. And it satisfies various symmetry properties, transitivity, homogeneity, and it satisfies a range of subtler properties, supersimplicity, and so on, which model theorists get very excited about, and which means that it's played a really central role within the model theory community since it was discovered, really. So, as I say, most people will know all about it. If you don't, then there's this nice survey paper by Peter Cameron, which I recommend. Okay, so I just wanted to observe that one can arrive at this structure, the Rado graph, via a few different possible routes. So the route I described is a sort of static thing. That is to say, one give yourself countably infinitely many vertices, and then do that wiring process all in one go. You can also think of this as an evolving process. Now, at this point, this may seem like a somewhat trivial distinction, but later it may not do. So to think of it as an evolving process, we could just add the vertices one at a time. vertex with the appropriate probability. And then at step omega, if you like, we get the graph we expect. It can also be arrived at by Frese amalgamation. This is very important, but not something I'm going to dwell on today. But then one other route is via what I'm calling for here the idea of a logical limit. So what this means is if you look at simply the finite graph, so GNP, where P is fixed and N is a finite cardinal number, so a natural number, then it was observed that we get a 0-1 law. What that means is that if you get any first order property in the language of graphs, so the simplest language one can use to talk about graphs really, then any first order property there has the property that if you look at whether these finite graphs are likely to satisfy it or not, the probability that they satisfy that property will either tend to 0 or 1, right? So large enough graphs GNP will either satisfy it highly likely or highly likely they won't. So you get this is a 0-1 law. And what one can then do is collect together all of the sentences which describe properties where that probability tends to 1. And you put them together, and we can give ourselves, call that a first order theory, and then look at a countable model of that theory, and we'll get the same graph again. Okay, so there you've got these different processes which arrive at the same destination. But by maybe slightly changing the changing some of these processes, we might end up in different destinations. Okay, so I'm going to now sort of change direction and look at the sorts of networks which arise in the real world. So what you can hopefully see, if the slide advancing button is working properly, then you can hopefully see a map of the internet. So this is a recent map created by the Opte project. And the idea is that every web page is a vertex on this graph. And then if there's a link from one page to another, then we connect them with an edge. And you get this rather beautiful picture arising out of it. Does this look much like an Erdős-Renyi random graph? Well, not a lot is the truth. And so what I'm going to spend a moment talking about some phenomena that arise in real world graphs. And of course, real world graphs and networks is a huge class. I mean, it seems ridiculous to try to generalize over that class. Nevertheless, there's a remarkable body of scientific evidence which shows what a lot of real world graphs look like, or what properties they have. So firstly, they tend to be sparse. Meaning that as the graph gets bigger and bigger, you just pick two random nodes. What's the probability that they're joined by an edge? Well, that probability goes to 0 as the graph gets larger and larger. And now if we think of the Erdős-Renyi process, that probability is always fixed at P, right? So the Erdős-Renyi graphs are dense. That is, they are not sparse graphs. So then there's a subtler one, which I'll revisit later, but it's to do with degree distributions. So if we look at the number of nodes of degree k, there's this strong finding that one is very likely to find what's called a power law. That is to say, the number of nodes of degree k strongly tends to be proportional to k to the minus gamma, where gamma is some fixed positive number for that process or for that graph. And that holds approximately for all k. The Erdős-Renyi graphs do not satisfy this. Okay. Then there are others. So the phenomenon of clustering, for example. Two vertices are more likely to be joined if they share a common neighbor than if they don't. And you know, think about the Facebook graph or something. What's the probability that two completely random people on Facebook are friends? Well, it's very, very small. If I then tell you that those two people have got a common friend, what's the probability now? Well, it goes zooming up. And that's the phenomenon known as clustering, which again is common in a range of real-world networks. And then another one, the small world phenomenon. So this idea of six degrees of separation you may have heard of. That you know, you're all of us are probably at most 5 or 6 handshakes away from the Prince of Wales or whoever it is you like. Okay, so those are some properties that real-world graphs and networks tend to have. And so what I'm going to do is, for the rest of this talk, I'm going to talk about these in turn, really, and talk about how the Erdős-Renyi model fails to really exhibit these, and think about what modifications one might make to that model. And really, as I say, the general idea here is a sort of two-way communication between model theorists and you know, network scientists, in the sense I described. You know, what are the sorts of processes that network science are studying, which maybe do exhibit these sorts of phenomena? Might those be of interest to model theorists? Or going the other way, what sort of objects or processes have model theorists got in their bag, which maybe could be interesting to network scientists? And I don't think that's a conversation which is at all far developed. I think, you know, really the point of this talk is that I think there is a conversation there to be had, and here are some sort of maybe small beginning parts to it. So in the rest of this talk, I'm going to take these in turn. I should say I'm aiming here for breadth rather than depth in this talk. So it's going to be I'm going to mention a number of different things, not in a huge amount of depth. Hopefully, people will find some of them interesting. Some of them are things I've been involved with myself. Towards the end, I'm going to talk about things which I'm not involved in. I just sort of find them interesting and they fit into this general picture. So that's my plan for the rest of the talk. So I'm going to start with sparsity, really. So we have in logic, we have a pretty good theory of sparse random graphs. And I think this hasn't really filtered through into sort of network science communities. I mean, I've talked to sort of complex systems type people about these things, and you know, they don't know anything about it. Okay, so I'm going to talk now about sparse random graphs. So this is the sort of key definition, and it's actually the same definition as before. So we have n nodes, and we wire them all up with probability p, but the difference here is that p depends on n. P is, in particular, it's given in this model here, it's given by n to the minus alpha, where alpha is some fixed positive number. And so you can see immediately that as n grows large, we're going to get sparsity arising. That is to say, the probability that two nodes connected tends to 0. So let me mention in passing here that what we've got when we do this, it's a sort of sequence of static graphs, right? You can do this on 10 graphs, on 10 vertices, and then you can do it on 11 vertices, and then you can do it on 12 vertices. But what you can't do is just sort of add a vertex to the 10 vertex graph to get the 11 vertex graph, right? At least not in any straightforward or natural way. So it's a sequence of static graphs. It's not an evolving process where one can sort of just let the graph grow, maybe sort of program it on a computer and let it grow node by node. Okay, so so the very nice fact here is that there is a 0-1 law, exactly as I described before, in this context too. So that is at least with the caveat that alpha should be an irrational number between 0 and 1. There are other sort of ranges of alpha which work too, but let's just focus on this one. An irrational number between 0 and 1. And then we get this 0-1 law. That is to say, any first order graph property, if you look at the graphs that arise from this, and then the probability that property is satisfied tends either to 0 or to 1. So then one can do this logical limit process. So you can gather together all of those first order properties where the probability tends to 1, and that's a first order theory. And then you can look at an infinite, well, let's say a countably infinite model of that first order theory. And I'm calling that a Scheller-Spencer graph. Okay, so these objects have been well studied by model theorists. These are well known in the community, but as I said, they're not very well known outside the community. And they're axiomatized by two axiom schemes, which I'm going to sort of wave my hands at. I mean, the first one we can go through in more detail. So it's a negative axiom scheme. It says that there are no dense subgraphs. Okay, what is a dense subgraph? Well, it's a graph where you've got too many edges. What's too many edges? Well, more than the number of vertices divided by alpha, essentially. So there are so the first part of the axiom scheme is that there are no subgraphs like that living inside this graph. And then there's a generic extension axiom, which is a positive axiom. It says things that do exist, that do happen. And I'm not going to go into all the details. You can ask me afterwards, I can talk about it. But I mean, the basic idea is that, so just maybe let's look at some parts of the definition. So for any tuple of vertices so start with any tuple of vertices, and any sort of way that you might want to extend those vertices, so that's a safe finite extension, then you can do that extension, and you can do it in a particularly nice generic way. That's the sort of the idea of this axiom scheme. I'm waving my hands. I'm not going into details because I don't want to, basically. Okay, so these are these Scheller-Spencer graphs. And model theorists are rightly excited about these. So these turns out to be strictly stable structures. That is to say, they're stable, non-superstable, and they're closely related to Krzyzewski constructions, which are objects which have been, taken a central role in model theory in recent years. Okay, so I'm going to now talk about something. Some work I did recently, and the idea here is that the Scheller-Spencer graph, as we've just met it, is a purely infinitary thing, right? The way one accesses it is by taking an countably infinite model of a first-order theory, essentially. So it's not something one approaches via a sequence of finite structures directly. So here's an adaptation of that. So we're going to fix a similar alpha. And then we're going to build a network one node at a time. So start with single node, and then at each stage we add on a new node. And just as we did with the Erdős-Rényi process, what we're going to do is wire up the new nodes to each previous node with the appropriate probability. But the difference here is that this probability changes now, because the probability is going to be t to the minus alpha, which is inspired by the Scheller-Spencer process. But of course, as t changes, that probability changes. So this is not an Erdős-Renyi graph or one of the finite graphs one gets thinking about Scheller-Spencer. So it's not that, but the question is, how different is it? How far away is it? Because I hope that this might be the sort of process which would be closer to something which might be of interest to people interested in real world graphs. Of course, you can imagine this process happening in the real world. So the result one gets is that if you run that process, adding one node at a time to its infinite limit, then the axioms of, well, we take the two axiom schemes of the Scheller-Spencer graph in turn. So the first one, remember, said there are no dense subgraphs. So that axiom fails, and you can, that's easy to convince yourself, because you can quite imagine in the small graphs that arise at the beginning, you might happen to get a dense subgraph. But there is a weakening of that graph, of that axiom, which holds with probability 1. So it relies on the idea of a rigid subgraph, which is a sort of strengthening of the idea of a dense subgraph. Again, I'm not going to give the formal definition. I can give it later if you like. So a strengthening of that definition, and any rigid subgraph, yes, it might appear inside that graph, but it's only going to do so finitely many times. That's the idea. So we don't get the no dense subgraphs axiom, but we do get a weakening of it. And then the generic extension axiom scheme, which I sort of waved my hands at, that continues to hold. That holds unamended. So it's not a Scheller-Spencer graph, but in some sense it's a Scheller-Spencer. The way I think of it is it's a Scheller-Spencer graph with some sort of random noise put on top of it, but not too much, hopefully. That's the idea. And these results also apply to sufficiently large finite stages of the process. Okay, so that's what I wanted to say about sparse random graphs. I mean, really, the idea here is that I think these Scheller-Spencer graphs, are known and loved in model theory, and I think they should be known and loved more widely. And this is my sort of initial attempt to do something to get them to be better known. But I'm sure there's more to be said there. Okay, so I'm going to move on.
Can I ask a question?
Yeah, sure.
So you mentioned a bunch of model theory type results like stability and so on for the Scheller-Spencer graph. Do you know things like that for this case?
I mean, it's a great question. I mean, the short answer is I don't know. I mean, I wouldn't expect I wouldn't expect any of those to hold in full generality. The question is whether there's some sort of interesting weakening of it that one could nevertheless say. I mean, I certainly wouldn't expect stability here, but might it be possible that one could nevertheless say something about non-forking in the structure? It's an interesting question. I don't think I have more to say about it than that.
Sure, no, fair enough. Thanks.
Thanks. Okay, so I'm going to move on. So I talked about degree distributions of within Erdős-Renyi random graphs and within real world networks. So this is on the screen here is a histogram that I've just run up on Python, just giving the degrees of a Erdős-Renyi graph with 10,000 nodes and probability p equals 1/2. You've got 10,000 nodes. How many other nodes would you expect a particular one to be joined to? Well, you'd expect it to be round about half of them, so round about 5,000. And you can see that indeed they are joined to round about 5,000. And furthermore, you get that sort of bell curve, and it's pretty tightly concentrated around that mean. I think that's the sort of key point I want to make. So, in the limit, it's a Poisson distribution, but it's tightly concentrated around the mean. In real world networks, you don't see much like that. That's not how they largely arise. So, for example, if you think of the internet, so the World Wide Web tends to be my sort of go-to real-world graph. There are lots of others, of course, but it's quite a handy one. So on the screen there, you can see a diagram that I've taken from a paper called "The Graph Structure of the Web Analyzed on Different Aggregation Levels" by Robert Musil et al. From 2015, and that graph is a log-log plot of the out degree of different web domains. So how many outgoing links there are. And you can see that it's there's the straight line, which is a pretty good fit to it. And that's illustrating that this power law that I mentioned. So the number of vertices of degree k is approximately proportional to k to the minus gamma, where gamma is some fixed number. What number is gamma? Well, in a lot of real-world networks, it's between 2 and 3. That seems to be a pretty solid experimental finding. For example, the web has it round about 2.5. And if you look at the so-called Kevin-Bacon graph, the collaboration graph of actors and so on, you get about 2.3. So it tends to be in that sort of number. So it's a very, very different sort of distribution than what we get from Erdős-Renyi graphs. So to try to improve, okay, so here's another picture. So on the left there, you've got an Erdős-Renyi model, which has got 1,000 nodes and turns out to have 355 edges. And then on the right-hand side, you've got a model produced by a different process called preferential attachment, which I'll come on to talk about, which happens to, just by good luck, it has, by design, it has 1,000 nodes, but by good luck, it has exactly the same number of edges, 255. But what you can hopefully see is that there are a few nodes in the right-hand graph which have got higher degree than anything you see on the left-hand graph.
Richard, can I just ask a quick question?
Yeah, sure.
Just to be clear, so the nodes here are on the circumference of the circle, is that right? That's correct.
That's correct. Yes.
Okay, right. That's fine. Thanks.
Yeah. So, sorry, I should have explained that. I tend to draw my graphs in circles. So yes, the nodes are around the circumference, and then there are the chords are the edges. So in the right-hand side, you can see a sort of a gathering where there are some nodes of high degree, higher degree. On the right-hand side of the right-hand graph than anything you see on the left. So you get a long tail. I think that's one sort of important takeaway from this power law is you get a long tail. You get some nodes of much higher degree than you ever expect to see in an Erdős-Renyi graph. Okay, so the Erdős-Renyi model wasn't really doing its job in terms of modeling these sorts of networks. And so a new paradigm, which was invented in 1999 by Barabasi and Albert, is called preferential attachment. And the key to it is this is a process where we add one node at a time and wire it up to previous nodes. But the key thing is that when we add the new node, whether or not we join it to a previous node is affected by the current degree of that previous node. So you often hear the phrase, the rich get richer. So nodes which have high degree tend to get even higher degree because new nodes are attracted to them. So that's the basic idea of preferential attachment. And there are a number of ways that you could sort of make that more specific. And here is what I hope you will agree is a fairly simple way of doing that. This is not the model introduced by Barabasi and Albert in their paper. I'll say more about that in a moment. It's a variant on that, but nevertheless, it has that same idea of the rich getting richer. I should say that this I wanted to mention in passing that this, if you look up this Barabasi and Albert paper on Google Scholar, you'll find it's got over 40,000 citations, which is it's more than whatever your favorite logic paper is. I guarantee that. So I only wanted to mention it. Just, of course, that doesn't really mean anything, but it does mean that there are really a lot of people out there who are interested in this sort of stuff. Okay, that's the point. Okay, so back to this process. So if we start with any old finite graph, and then so suppose we've got now a graph at time t with t vertices, and at time t plus 1, we're going to add in a new vertex, and then we look at each existing vertex and we connect the new vertex to that existing vertex u with probability given by the degree of u over t minus 1. Degree of u in the previous sort of stage, if you like. Why over t minus 1? Well, if you think in a graph of t vertices, what's the maximum degree that any node could have? Well, it's t minus 1. So this is, we're just attaching according to that, the sort of the most simple-minded, really, probability that we could. So the degree of u over t minus 1, and we do that to all the existing vertices, and we carry that on. Okay, is that model fairly clear? Hopefully, it seems sort of reasonably straightforward. Anyone shout if that's not clear? Okay, so then thank you for the thumbs up. Okay, so then this is somewhere where the question I ask is, what do you get at the infinite limit of this, right? And that's not necessarily a question which springs to the mind of sort of more real world based network scientists, but so it turns out that this that one can predict pretty well what you get at the infinite limit of this. So let's just observe that if at any stage we have a node of degree 0, then the probability that any further node joins to it is 0, right? So if a node has degree 0, then it never gets any more, its degree never grows. So a node of degree 0 is stuck at 0. And likewise, if you happen to have a node which is of maximal possible degree, then the probability that subsequent nodes join to it is 1. So again, and then that carries on forever. So you've got these sort of potentially exceptional nodes with of degree 0 or of maximal possible degree. So I call those isolated nodes or universal nodes. If you happen to start this process on a graph with no edges at all, just a few vertices scattered around, then it's a very boring process because you never add any edges, right? And likewise, if you start it on a complete graph, then you add all possible edges at every stage. So those are rather uninteresting situations. But so long as you don't do that, so long as you start it on a graph which is not edgeless or complete, then with probability 1, what you get at the infinite limit is a copy of the Rado graph plus a finite number of either isolated vertices or universal vertices joined to everything. And of course, you can't have both isolated vertices and universal vertices, right? Because if you've got a universal vertex, then no other vertex can be isolated. So it's one or the other. Okay, so on the one hand, I was quite pleased with this result because it takes what seems to me to be a sort of fairly natural interpretation of quite an important process, and you do something natural, you run it to infinity, and you get something we know and love at the end, the Rado graph. So I was quite pleased with it. On the other hand, from the sort of point of view of modeling real world phenomena, this is not a useful fact to know because the Rado graph is so full of symmetries and homogeneity that actually it loses all local structure completely, right? So, I mean, it's sort of interesting that all local structure completely disintegrates, but if you wanted to, so a fairly natural thing to do with an infinite graph is to use it as a model for a very large finite network. But this is not a useful approach to that because, well, because it's not a useful model of anything really, because too much happens. Everything, it's the Alice's restaurant phenomenon. Everything is possible, which is not a good model. So, I've talked to sort of network scientist types about this theorem, and I went up to them all eager-eyed and excited, and they sort of shrugged their shoulders really. But so there's a question then. So I know that this result doesn't. So the result I've just described is for just one particular process, right? There's no sort of wiggle room at all. One could look at variants of it where one multiplies that probability by some constant which is less than 1, sort of dampening down the probability. That seems a sort of fairly natural thing to do. If you think this graph is too dense, and indeed it is too dense. And I know that this result does fail. So I know that you won't get, with probability 1, you will not get the Rado graph. But what do you get? I don't know. And I wonder if there's anything interesting to say there. Okay, so I'm going to move on, but not very far. I'm going to talk about some different approaches to preferential attachment. So I was not the first person to come up with the idea of taking the infinite limit of preferential attachment. So the original model proposed by Barabasi and Albert, well, actually, there's a little bit of ambiguity in that paper, but it's probably closest to something like this. Let's just fix some function which gives a natural number at each stage. And we're going to build a di-multigraph. That is to say, directed graph. So the previous stuff I was talking about was just about undirected graphs. A directed graph, and also a multigraph. That is to say, a multigraph is where you're allowed parallel edges connecting the same two vertices. So at step 1, we're going to build just a graph with 2 vertices and f naught many edges connecting the first to the north. And then we're going to continue the process, adding a new vertex at each step with f of n outgoing edges. So the key difference to the previous model I just discussed is that the number of vertices that you get at each step is given in advance, right? This is not something that arises as a random variable, it's given in advance. So, but of course, where they go, where those vertices, where those edges end up, the endpoints of them is random, and it's chosen. So each of those edges is then chosen between the existing vertices, again according to their degree, according to this this ratio here. So the degree of the vertex in question over the total degree of all existing vertices. And of course, you might find that more than one edge goes to the same vertex, but that's allowed in this model. Okay, so is that model clear? It's a little bit more complicated, but as I say, it's closer to the Barabasi-Albert original preferential attachment model. And so the paper, which was sort of my entry point into these questions, and it was the first one that I'm aware of to look at the infinite limit of these processes, was a paper by Robert and John Kleinberg in 2005. And so what they show is, if let's just take a simple case, suppose we're just adding, if f of n is constantly 1, so you just add one edge at each time, right? then with probability 1, I can tell you exactly what structure you'll get at the infinite limit. And on the other hand, if the function is constantly 2, then the same goes. With probability 1, there's a limiting structure which with probability 1 will arise. And those structures, have been axiomatized. Again, I'm not going to go into the details, but they're well understood exactly what they look like. On the other hand, if f is not constantly 1 or 2, then there's a positive probability that when you do this process twice, you'll get non-isomorphic structures, at least as directed multigraphs. And they also show that even if you forget the directions, right? So just look at it as an undirected multigraphs. If f is constant, but not either 1 or 2, then the same holds. With probability, positive probability, you will get, run it twice, you'll get different structures. However, you might notice a possible little loophole there, which is that, so if f is non-constant and you're forgetting directions and just looking at multigraphs, then there's no implication as to what arises here. So they don't have anything to say in that case. And so there was that loophole had, to me, something quite interesting lurking in it. So here's a so going sort of far away from the process where we're adding a constant number of edges each time. If instead we let the number of edges grow linearly, so if f is bounded above and below by linear functions for all large enough n, then with probability 1, again forgetting the direction, so just looking at multigraphs, I can tell you exactly what will arise at the infinite limit up to isomorphism. And what is it? It's a structure I call the Rado multigraph. So it's a sort of natural multigraph analog of the Rado graph. And again, I'm not going to give you its definition, but if you're interested, I can do, or alternative, you could probably try and guess, and you'd probably guess right. Okay, so again, this is a sort of result that I found quite sort of aesthetically pleasing, but the same caveat arises as before, which is that this is far too dense a structure to be of any use for modeling any real world phenomenon probably. And of course, the Rado multigraph has far too many symmetries and homogeneities and so on to tell us anything useful either. So then there's a question here: might we be able to say anything interesting about sublinear but super constant growth? Question. Right. Okay. So for the final 10 minutes or however long I've got, I'm going to talk about a few other things. So I think I should stress that at this point in the talk, I'm talking about things that I find quite interesting that I'm not expert in. So things that should appear in a talk on this theme, but I'm not. I hope you find them interesting. I think that's what I could say, really. Okay, so but I think an important thing to mention is this idea of clustering. So one can get a clustering coefficient for any graph by essentially looking at the number of places where you've got two sides of a triangle and the number of places where you've got all three sides of the triangle, and taking the ratio of the second of those to the first. So, that's telling you how likely are you to close off that, to finish off the triangle. And because in real world networks, the answer is you're often quite likely to. Real world networks do exhibit clustering in this sense. The Elwes graph, of course, doesn't. The third side of the triangle is completely independent of the other two, so you're no more likely to get an edge there than anywhere else. Okay, so there's a big area that I'm just going to gesture in the direction of, and this is geometric random graphs. So so this is a graphic that I generated in Python, and what it is it's a unit square where I've put n vertices scattered at random. Well, n here is 200. And then I've picked a particular number to be the radius. And the idea is that if two vertices are within that radius of each other, call it the radius of connectivity or something, then we join them with an edge. And if they're not, then you don't. So the entire structure of this graph is determined by the geometry of the plane. Now, geometric random graphs are a really big and important area of study, and they tie into via areas like percolation theory. They tie into practical applications, statistical mechanics, and all sorts of interesting areas. I'm not an expert, so all I wanted to do is sort of gesture that there is this big and important field out there, and the model theory of it, I think, is now coming along as well. But rather than talking about that, I wanted to say a slight variant on this thing, which I came across recently, which I thought I'd like to mention. So this is an alternative approach to geometric random graphs. So let's take a metric space, and so for example, it could be the plane, and take a countable dense subset in it. And then we've got some fixed probability measure. And then we're working here with a radius of 1. And for two of our vertices within that vertex set, if their distance is less than 1, then we toss our coin, Elwes style, and we connect them with a vertex with an edge, or not, according to the coin toss. So so this is different from the model I just described, because there is this probability there's this probability aspect of it. So the previous model, the randomness was in scattering the points, and then if they were close enough, they were joined. Whereas here, then if they're close enough, then you toss a coin to see if they're joined, essentially. But you're starting with a sort of given countable dense subset. There are all sorts of other possible random geometric graphs which have been studied in depth as well, I should say. So, for example, you could just scatter your points around the plane and then connect each node to the 10 nearest, for example, however far away there are. So there's lots of variants possible, and they have been investigated in some depth. But I just want to spend a moment on this, because there's some interesting logic that comes out of it, which I'm not at all involved with or expert on, I should say. So any mistakes are mine. So if you do this process twice, so you start with your countable dense subset, and then you do this coin tossing process for the graphs which are near each other, then if you're doing well, it depends. What happens in them? It depends on what in your metric space. I think that's a really key thing. So different metric spaces behave differently. If you're in the real numbers, then with probability 1, you'll get the same outcome each time. If you're in the plane, though, with its usual Euclidean Pythagorean metric, then with probability 1, the two outcomes you get will be non-isomorphic. So that's a result of Anthony Bonato and Janet Janssen from 2011. But there's some new work which I heard about recently, which I thought was quite interesting, which says that nevertheless there is a first order theory of a graph lurking here, even though the graphs will be non-isomorphic, they will nevertheless, with probability 1, in this instance, be not elementarily, but elementarily equivalent, so the same first order theory. So then, this opens up a lot of interesting questions as to what this first order theory is, and to what extent one can recreate the geometry of the situation back from the theory of the graph. So if you think about what this structure looks like, within a small ball, it looks like a copy of the radograph, right? Because it is. It doesn't look like it is a copy of the radograph. But those lots, copies of the radograph are sort of spread together across this geometry. And so there's a really interesting, I think, field emerging here where and logic really does seem to have something powerful to say about it. Okay, so then I'm just going to end by mentioning in passing a couple of other, and then I'll be quiet, a couple of other processes that network scientists use to generate real models for real-world graphs, in particular models which exhibit clustering. So this is a duplication model. Just it's a pretty simple thing, really. We've got some probability measure, and at each stage we add a new node, and then we select a previous node uniformly at random. And then we look at that, that's the target node. And then you look at each neighbor of the target node, and with probability P, you connect your new node to each of those neighbors. So the point is you're copying neighborhoods, essentially, or maybe bits of neighborhoods. And that's in some sense quite a natural model. And it seems to be a particularly good model for a number of biological networks, so protein interaction networks within cells. Again, I'm hugely far from being an expert on this, but it's a nice simple model. It seems seems so natural and straightforward. And I thought I'd just sort of throw it in as an interesting thing you might like to hear about. And the same goes for the final thing that I'm going to talk about, not in any depth, just because I don't think I could give this talk without mentioning this. This is the Watt-Strogat model. It's a celebrated model of networks in the real world. It's got the paper in Nature has got even more citations than the Barabasi-Albert paper. And again, it's a really nice, simple thing. So you start with n nodes arranged in a circle. And you've got some number k, which is basically the neighborhood size. So let's say it's 10, because it is 10 in the picture. So you then join your each node to the 10, and to the 5 on each side. So 10 in total. So you can see there's a sort of, in this picture, there's a sort of fixed rim around. That's because each node is joined to its 5 neighbors on each side. So that's a fairly boring thing. But then what makes it interesting is that there's this rewiring probability. So there's some fixed number beta, which is a rewiring probability. Then you sort of go clockwise around, and you look at each node, and you look at each edge coming out of it. And with probability beta, you rewire it. So you take the far end and you just put it to a uniformly random chosen place. And the point of this model is that you get the small world. That is to say, in fact, you get the small world and you get clustering. So before you do this before you do this rewiring, of course, you've got lots of clustering, right? You've got loads of triangles because everything's joined to all its neighbors. But once you do the rewiring, you keep the clustering, assuming beta is not enormous, but you also get the small world network. So that is to say, you know, the journey from any node to any other should be small, because you've got these shortcuts cutting across the disk essentially. So this is a model which has seen, you know, a huge amount of use for people modeling all sorts of real world phenomena. So you get the cluster, you get the small world, but you don't get the power laws. So the degree, you know, the degrees are fixed throughout. So, you know, there's trade-offs and there's all sorts of different models in play. Okay, so I'm sorry, the end of that talk was sort of rather rambling. I just sort of wanted to show you a few things that I thought people should see, really, and I think I'll stop there. Thank you.